In today's session, we'll talk about using biometrics, Gait for security applications. So thank you everyone for spending your time with us this afternoon. This morning, welcome to this presentation on using Gait for security applications. My name is Noor and I'll be presenting for you today. So here's some information about myself. I'm a cybersecurity instructor at Bow Valley College. I have my master's degree from the University of Calgary, and I have the IBM Mastery Awards for Application Security Engineer and Security Intelligence Engineer. So at Bow Valley College, we teach this program, Cybersecurity Post-Diploma Certificate. And this program has two semesters, so it's like 2 terms. So in the first term, we are covering some of the topics such as information security, endpoint security, network security, cryptography, and so on. And in term 2, we will be covering vulnerability management, advanced network security, security exploits, and network defense, introduction to cloud security, and so on. So if we look at the job marketplace for cybersecurity, we can see that a great way to enter that marketplace is by acquiring all these certificates. So through our program, we'll try to cover most of the topics for these certificates. The courses in the program will prepare you for the responsibilities you will have to take as a cybersecurity professional. So as I said, these certificates are essential tools for IT professionals in the job marketplace nowadays. So these are just few of them. Of course, there are lots of certificates, but we are just covering these some of the topics, most of the topics of these certificates in our program. So in this slide, we have the objective of our session. So we'll go through authentication, authentication credentials, biometrics, and gait analysis. Authentication. So our first topic will be authentication. In information security, authentication is the process of ensuring that the person or a system desiring access to resources is authentic and is not an imposter. Authentication is an essential element of IT security and can never be taken lightly. In information technology, IT, these 5 elements are known as the authentication credentials. Although there are many different authentication credentials that can be presented to an IT system to verify if the user is genuine, all credentials can be classified into one of these 5 categories. We can see these credentials here from this slide. What you know, for example, a password. What you have, an example of that would be a token, or maybe your cell phone, or the smart card. What you have, what you are, for example, biometrics, like the face biometric, the iris, and what you are, for example, the geolocation, and what you do, the behavioral biometrics, for example, Gait. Before we talk about these 5 authentication credentials, let's talk a bit about multi-factor authentication and single-factor authentication. So when a user is using more than one type of authentication credentials, we call this a multi-factor authentication. For example, what a user knows, like a password, and what a user has, for example, the token, could be used together for authentication. Single-factor authentication is just using one type of authentication. So of course, we should go with multi-factor authentication using more than one type of authentication credentials. What do you know? As an example of that, we talked about the password. So we said password. Password is a secret combination of letters, numbers, and or characters that only users should have knowledge of. Passwords are by far the most common type of authentication used today based on something you know that no one else knows. So when the user logs into a system, the system will ask the user to identify. The user will identify using the username, and then the user will be asked to authenticate by using a password. Weakness of passwords is linked to human memory. So humans can memorize only a limited number of items. Long, complex passwords are most effective but most difficult to memorize. Each account password should be unique. Users must remember passwords for many different accounts. Security policies mandate password must expire. So here are some tips for using a password. Never use the same password across accounts. Even more importantly, never reuse personal account passwords on work accounts or devices. Consider using a password manager. Try to create a passphrase rather than a single word or a number series. And also do not use work devices for personal business. So we are done with what you know. Let's talk about what you have. And we said an example of that are the tokens, the smart cards, the cell phones. So let's talk about the tokens. Another type of authentication credential is based on the approved user having a specific item in his possession. So something you have. Such items are often used in conjunction with passwords. An example of that would be the token. So the token are used to create a one-time password. They call it OTP, one-time password. Authentication code that can be used only once or for a limited period of time. This code will be generated from an algorithm and will be changed every 30 to 60 seconds. Token code changes frequently. Attacker would have to crack code within the time limit. User may know if a password has been stolen. If token is stolen, it becomes obvious and steps could be taken to disable account. We can also use smart cards. So instead of tokens, we can use smart cards. And these smart cards, just like smart cards, contains integrated circuit chip that holds information. Or we can use a cell phone. So cell phones are increasingly replacing tokens and cards nowadays. A code can be sent to a user's cell phone through an application on the device. What you are. Biometrics uses a person's unique physical characteristics for authentication. For example, face or hand or eye characteristics. We use special scanners for these characteristics. For example, iris scanner. So the iris scanner, which can use a standard computer webcam, uses the unique characteristics of the iris, which is a thin, circular structure in the eye. The iris is responsible for controlling the diameter and the size of pupils to regulate the amount of light reaching the retina. Iris recognition identifies the unique random patterns in an iris for authentication. A biometric authentication that is becoming increasingly popular on smartphones is facial recognition. So nowadays, facial recognition is widely used. Every person's face has several distinguishable landmarks that make up their face features. Where you are, geolocation. It's the identification of the location of a person or object using technology. Authentication through geolocation is increasingly being used for mobile devices, but as with laptops and desktop computers, it is often used to exclude imposters or raise an alert about a potential unauthorized user as opposed to authenticating a user based exclusively on location. What you do, an example of that is the behavioral biometrics, such as the Gait. So behavioral biometrics authenticates by normal actions the user performs. Another example would be the keystroke. So keystroke dynamics attempts to recognize users' typing rhythm. All users type at a different pace. It will provide up to 98% accuracy. We talked about also, we mentioned Gait. So in the next few slides, we will focus on Gait as a behavioral biometric. Biometrics. Biometrics is the field of study concerning measurement and analysis of the human body and its physical and behavioral characteristics. Biometrics include physical, physiological features such as face appearance, fingerprint, iris measurements, as well as behavioral features such as signature, voice, and gait. And in this session, we will focus on gait analysis. Human gait is a significant indicator of the health of an individual. We can use gait to detect and classify gait abnormalities, for example, asymmetry. Or we could also determine the level of severity of any detected abnormalities. Gait can be categorized as soft biometric. Other examples of soft biometrics include facial expression, age, or gender. Gait is defined as an individual's locomotion pattern, their manner of walking. So observing an individual's gait is not a novel concept. It has been already studied and applied in the field of medicine and also in the field of in border control. The most relevant application of biometrics has been for the identification of individuals for security or forensic purposes. Biometrics has also been applied in the healthcare sector and has shown a great potential for accurate pathology diagnosis, monitoring the health status of patients, and detecting intoxication. Biometrics work in the healthcare sector involves acquiring and verifying measurements related to the area of concern and analyzing these measurements to detect deviations from the normal range of patterns. Using biometric traits to identify and diagnose patients is becoming increasingly more relevant in the healthcare field. Some of the traits that can be measured are the face, as we said before, the fingerprints, iris, gait, and the voice. They are used as a tool to reduce the chance of falsely identifying someone, for example, in the border control. Gait is one of the biometrics that can be utilized to distinguish individuals based on human walking style from large distance and without the user's cooperation. An example here, if you can see from this slide, biometrics, we can use biometrics for health applications. We could use it as well for border crossings check. Biometrics or gait for health applications. So as we said before, human gait is a significant indicator of the health of an individual. Gait data can be used for diagnosis, monitoring, and rehabilitation. Gait analysis aims at detecting the individual's gait features and can be used to determine gait type and diagnose pathology. For example, stoppage or spastic gait. In healthcare applications, changes in gait provide key information needed for the detection of health deterioration in the elderly or symptoms of various diseases, including, for example, neurological diseases, for example, multiple sclerosis or Parkinson's diseases, and systemic diseases such as cardiopathies. Monitoring and evaluation of the gait characteristics over time may enable early diagnosis of such diseases and help prevent future health problems. How about for border crossings? For applications such as border crossings, one important function is to search against an existing database or watch list. So for example, in the airport, there should be a database or a watch list. Contemporary watch list screening technology uses alphanumeric data such as name, date, and place of birth, which are not reliable records, as they can be forged or obtained using fraudulent breeder documents. To mitigate this problem, watch lists used in forensic applications may be used. They include records about soft biometrics. And when we say like soft biometrics, we mean, for example, the gender, the height, the weight, or the gait characteristics. So assuming that facial data is recorded during a traveler's passage through border control or a less controlled environment will result in a low matching score. But when traveler's gait data is also compared against an existing database, the rate of correct identification increases greatly. So let's discover the general method to detect and analyze gait abnormality. So during my master research at the University of Calgary, we examined the following. So we have this approach, and we have used this approach. It's the gait recognition approach. So first, we acquire the data. We get the data from a camera, which is a Connect camera in this image here. And then we process the data, we extract the features, and then we do the classification. So to protect the privacy of a participant, we chose to go with the skeleton frames. If you can see from this slide here, this is samples of the frames provided by the Connect camera that we have used. So we've got RGB frames, depth, and also skeleton. So to protect the privacy of our participant, we have chosen to go with these skeleton frames. So we got the input data, as you can see from this image here. So the gait depth data was provided by no marker gait data acquisition using the Microsoft Connect. So from the skeleton frames, we got these vectors here. So for example, for each joint, we have the foot joint position. So for each joint, we will get the X, Y, and Z coordinate, and we will deal with just numbers to protect the privacy of our participants. We were just using numbers and analyzing these numbers or vectors. So as you can see here, this is for the left foot. The same thing will be for the right foot, for the left ankle, right ankle, and so on, for all the joints. After we got the data, we processed the data. We were just smoothing the erratic values from the data. And then before we started to extract other features, we extracted the gait cycle. So we have used two methods to extract a gait cycle. These two methods are, as you can see in this slide, joint relative angle, JRA, and joint relative distance, JRD. So two methods of gait cycle detection were used. In the first method, the joint relative angle, this one here. So the joint relative angles, JRA, of the subject's ankles were used to observe the events between two consecutive heel strikes of the same foot. The first heel strike is the beginning of a gait cycle, and the second heel strike is its end. So we call this a heel strike here, the first image. And then this is foot flat, and this here is a toe off. So the gait cycle will start with the first heel strike, and then will end with the second heel strike. So as you can see, there are 8 phases, but the 3 major phases are here. So heel strike, foot flat, and toe off. So the ankle angle is a measurement of the ankle relative to the vertical plane of the leg and not the angle between the arch and the shin. In the second method, the distance between the left and the right ankles was calculated for each frame, also known as the joint relative distance, JRD. And the gait cycle was found by determining 3 consecutive local maxima when the subject's feet are furthest apart. The mean maximum JRD was 0.2 meters. However, this mean was subject to a high variation between individual subjects. After we got the gait cycle, we were able to extract other features. For example, the static feature extractions, such as height, the arm length, leg length. We were able to extract dynamic features such as knee and shoulder movements, cadence, and stride length. In this slide, we have the shoulder joint positions and knee angles for normal and abnormal gait, and we'll talk about these figures in the coming slides. We have used different types of classifiers, such as the LDA, SVM, MB, KNN. So many algorithms have been used for classification. So let's start with the experimental procedures and results. In the first experiment, we examined the feasibility of using the lower body joint data, for example, the knee angles and the ankle angles, to classify gait type. So we have get the images like from the user when they are walking, for example, in the airport. So we get the images, the RGB depth camera. We'll go through the gait trait analyzer, semantic form, and then it will be compared against a database. So let's say in the airport, they have a database of face, fingerprint, and other characteristics. There's inference engine here, and we will have the decision at the end. So as we mentioned before, the input data here, we were dealing with just the vectors like the X, Y, and Z. For example, here for the left foot, left knee, right knee, left ankle, and so on. So we do some processing, we smooth the data, and then we do the feature extraction. Then we use the classifier to distinguish if this is a normal or abnormal gait. So by using the knee angles, we were able to distinguish between a normal and abnormal gait. So after plotting the data, we find out that for a person with a normal walking motion, the knee moved in a predictable range from straight 180 degree to well below 150 degree. As you can see here, this is a normal gait. So from 180 to well below 150. For persons with abnormalities in walking motion, one of the knees could not bend below 150, as you can see here in this figure, okay? And had a range of movement that was considerably different from the other healthy knee. So we were able to distinguish between a normal gait and abnormal gait using the knee angles. We have used many classifiers, as I mentioned before. These are the accuracy rates of the classifiers. So in summary, the proposed gait trait analyzer was able to detect and classify gait abnormalities. Now we find out that the KNN classifier was the best of all traditional classifiers. So after we finished with the upper joint body, we moved to the, after we finished with the lower body joint data, we moved to the upper body joint data. For example, the shoulder movements. So after determining if the person have a normal or abnormal gait, if the person has abnormal gait, let's check the severity of the abnormalities. So we have used the shoulder movement for that. If you can see here from this figure, we got the input data, we processed this, the same procedure, we extracted the features, and then we have used the classifiers to determine if we have a moderate gait abnormality or extreme gait abnormality. We theorized that having a limp would cause abnormalities in the upper body movement, such as an abnormal shoulder movement pattern. So 3 categories are used to define the results: normal motion, moderate abnormality, and extreme abnormality. We can see the difference here. So for example, the y-coordinate of the left shoulder and right shoulder joints for a normal gait, it's like that. But for abnormal gait, you can see the difference here. So you can see the y-coordinates of the left and right shoulder joints. There is a difference between them. Here are the classifiers that we have used and the accuracy, right? So in summary, the proposed framework was generally successful in identifying gait abnormality and also determining the severity of this abnormality. The novelty included usage of the upper body features to determine severity of gait abnormality and usage of a dynamic Bayesian networks as a classifier. The accuracy rate was 82.19% of the DBN classifier. The third experiment, or as you can see here, is kind of different. So with this one here, we use the fusion. I'm sorry, there's a typo here. So it's the third experiment. We have used the fusion of gait characteristics with the facial scores, okay, and height measures to recognize an individual's identity. So we can use this at the airports, for example. So this system functioned by comparing pre-selected facial features obtained from an image or maybe a video frame with a database of facial images to look for commonalities and identify that individual. So we can see here, for example, if a person that's going to the airport, his height is 170 and his gait type is normal. So this will be compared with a database. So here we have a database that has the height, gait type, face data, and the face characteristic as well. So first, for example, we'll check the height, okay? So this person height is 170. If we have, like, for example, 2 people with 170, then we just have 2. So from this list here, we just continue with these 2, and then we check. So the gait type is normal. We go to the gait type. So this 170 here is normal. This 170 here is abnormal. So of course, we'll go with the normal one. And then we will have the face scores. With all this information, we will be able to identify the person. So we were able to improve the recognition rate of facial recognition system by fusing it with gait and height. So in conclusions, after all these experiments, we find out that derived gait features can be used to distinguish between different gait types. Gait can be also fused with other modalities to increase performance of biometric recognition. Okay, so that's all with me. I would like to thank you all for spending your time with us this morning. I hope you enjoyed the session. Thanks to all the people who supported the conference as well. So let's open it for, I would like to open it for any questions. Okay, let's see here. Yeah, so I see from Christopher, the health diagnostics applications are cool. It would be interesting to have a smartwatch. Of course, we could use the smartwatch, but these are wearable devices. So in this research here, we just used the Connect camera. So we didn't want to have anything on the participants. So we didn't use any wearable devices, but of course, there are many research that have used the wearable devices. What if a bad actor is on the list, but something inhale or food with the something inhale? So with the Connect camera that we have used, it will just we will just get the joint position. So even if someone is wearing like a heel, then we just get the it just will capture the joint location. Have you considered the impact of devices such as offloader braces and others that would change an abnormal gait to a normal gait? We haven't considered the impact of these devices. These are like wearable devices. Thank you so much. We enjoyed a lot, but only in one foot. No, so we are capturing the data on, so for example, foot left, foot right, left ankle, why I'm doing the opposite, left ankle, right ankle, left knee, right knee. Okay, so we got all the joint positions from the camera, and then for the lower body, we have used the knee angles to determine if the person has a normal or abnormal gait. And then after that, we added the shoulder movements to determine the severity of a person that's having abnormal gait. Any more questions? Do you see practical applications for physical security, delta in gait and facial patterns between entry and exit of a facility, post prevention, that scenarios, others? So for now, to see the impact of the various braces, as they are very form-fitting and not easy seen anymore. Yeah, I agree. And so in our research, we just try to see the feasibility if we can use like these characteristics. In addition, so right now, for example, in the airport, they are using already the facial recognition, but we wanted to add other features to help identify people. So we were checking the feasibility of adding, for example, gait characteristics and the height as well of a person. But of course, we could use other characteristics as well. Okay. So thank you, everyone.